magnetic force between magnets. In a bar magnet, there are two magnetic poles. One end is north pole and the other end is the south pole. If two like poles facing each other, then they will be repelled. However, if opposite poles facing each other, they will attract. Therefore, like poles repel and unlike poles attract. Magnetic field lies around a magnet. There are two ways to find the magnetic field patterns around a magnet. The first way is using iron filings to plot the magnetic field pattern. The steps are: first, place a cardboard over a bar magnet. Next, sprinkle iron filings evenly on the cardboard. Next, slightly tap the cardboard. Lastly, the pattern of the iron filings shown on the cardboard represents the magnetic field patterns produced by the magnet. The second way, using compass to plot magnetic field lines. Notice that magnetic field lines flow from the north pole to the south pole. The steps are: first, put the bar magnet on the paper. Next, put a small compass near the magnet. Third, use arrow to draw the line aligned with the compass needle. Next, repeat the above steps to plot the magnetic field lines at different positions, as shown in the diagram. In this diagram, we have the compass needle's directions shown, and let's see some examples of magnetic field lines between magnets. First, when two bar magnets with opposite poles facing each other, using iron filings, the magnetic field patterns will be shown in this diagram. Since magnetic field lines flows from the north pole to the south pole, therefore the magnetic field lines can be plotted as shown. Second, if two bar magnets with the same pole facing each other, if the north pole and the north pole face each other, then the magnetic field patterns shown by using iron filing is this one. And the magnetic field lines around the magnets will be this one. Notice that at the point where there is no magnetic field lines, this is called neutral point. At this point, the resultant magnetic field is 0. Next one, when two slab-shaped magnets with opposite poles facing each other, as shown in the diagram, and we use the cardboard above the magnets, and using iron filings, we can find the magnetic field patterns as shown in this diagram. And the magnetic field lines is parallel from the north pole to the south pole, and it is uniform. Let's see the magnetic field lines around current carrying conductors. The first one is a long straight wire. When a current passes through a long straight wire, the wires will produce magnetic fields around it. By using right-hand grip rule, the thumb points along the direction of the current. While other fingers give the directions of the magnetic field, which is circular magnetic field. The grip rule can still be applied no matter what is the direction of the current and the position of the wire. For a long straight wire, the magnetic field strength, or we say the magnetic flux density, B, is equal to mu naught I over 2 pi r, where mu naught equal to permeability of free space, which is equal to 4 pi times 10 to the power -7. And I is the current. R is the distance from the wire. Consider the side view. If current is upward, by using right-hand grip rule, the magnetic fields produced by the wires on the right-hand side is into the plane of the paper, while the magnetic field on the left-hand side is pointing out of the paper. If the top view is observed, the current is pointing out of the paper. By using the right-hand grip rule, we have circular magnetic field produced by the wire, which flows in the directions anti-clockwise. For a solenoid is made by winding a long wire in a number of turns. When a current passes through a solenoid, the magnetic fields inside the solenoid is found by using right-hand screw rules, as shown in the diagram. The other fingers represents the directions of the current I, while the thumb points in the directions represents the directions of the magnetic field lines inside the solenoid. When the current passes through the solenoid in the direction shown here, I, by using the right-hand screw rules, we have the magnetic field lines inside the solenoid will be and the pole on the left hand side will be the north pole, because the direction of the magnetic field lines are away from the north pole and towards the south poles. Notice that the polarity at the ends of the solenoids depends on direction of currents only. Notice that the magnetic field strength inside a solenoid, or we say the magnetic flux density inside the solenoid, is uniform, and with magnitude B equal to mu naught N I over L, where N is the total number of turns, I is the current, L is the length of the solenoid. Electromagnet. Electromagnet is made by winding a solenoid around an iron core. When a current passes through the electromagnet as shown in the directions of currents as shown in the diagram, by using the right-hand screw rules, the direction of the magnetic field lines inside the electromagnet is towards the left. Therefore, the left pole is north pole and the right-hand pole is south pole. However, if the direction of currents is reversed, then by using right-hand screw rules, we have inside the electromagnet, the magnetic field lines will be from the left-hand side to the right-hand side, that is towards the right. In this case, the left pole is south and the right pole is north. Note that direction of currents only affects the polarities of the electromagnet, but not its strength. The magnetic field strength of an electromagnet can be increased by winding more turns on the iron core N, or increase the current I. Use of electromagnet. The examples is electric bell. Look at this diagram. When the switch is closed, the current flows in the electromagnet and the metal part M is attracted towards the electromagnet. Therefore, the hammer will hit the thorn and produce sound. And because the metal part leaves the contact C, no current will flow again. Then the electromagnet does not work. When the metal part returns to its original position, the above process are repeated and a series of sound is produced. The sound loudness can be increased by increasing the current or by using more turns in the electromagnet. And the pitch of the sound is determined by the nature of the thorn. That is, depends on the material of the thorn or the mass of the thorn. Electromagnet can also be used to attract metals, as shown in the diagram, or can be used in magnet trains, 磁浮列車. Magnet trains use powerful electromagnets under the cars to float above a track by creating a magnetic field between the train and the track. The magnetic fields created by the coil in the guideway, 路軌, and the track combines to propel the train. Therefore, the train can float in air. When a current passes through a circular coil as shown in the diagram in the direction shown, by using the right-hand screw rule, the other fingers represents the direction of currents and the thumb points in the directions of the magnetic field strength inside the coil. Therefore, the magnetic field lines will be represented by the diagram